So we are finally able to talk about ideal gases. So in a gas sample, if the temperature is high enough and the pressure is low enough, all gases behave the same way. And they all behave ideally. Which doesn't sound terribly helpful, but I promise we're getting to the important information here. So if a gas is behaving ideally, it will follow the guidelines that I'm going to list here. So ideal gases. In an ideal gas, the volume of the gas molecules is negligible. So in comparison to the free volume in the sample, the volume of the actual particles of gas is so tiny that we can ignore it. In a sample of an ideal gas, the molecules exhibit continuous random motion. And the molecules are non-sticky, hard spheres. So when they run into each other, or when they run into the sides of the container, we'll get purely elastic collisions, just to bring up a little bit more physics. And we will talk about what that means in a later video on kinetic molecular theory. So there are several underlying laws that ideal gases behave. So ideal gases obey several laws. So Boyle's law is that P1V1 equals P2V2. So essentially, it's saying that the pressure and the volume are directly proportional to each other. And so if you have a sample with a given volume and a given pressure, if you change the volume, you can calculate what the new pressure would be, or if you change the pressure, you can calculate what the new volume would be. Charles' law is V1 over T1 equals V2 over T2. So now, if you know the volume and the temperature under one set of conditions, if you change the temperature, you can calculate the new volume. Or if you change the volume, you can calculate what the new temperature would be. And then the last one is Avogadro's law, and it is the same Avogadro. So it won't surprise you that moles are involved here, and that this law says V1 over N1 equals V2 over N2. So in all three of these, anything not listed is held constant. So in Boyle's law, we're talking about pressure and volume, so the temperature and the number of moles are held constant. This is what we mean by this. Also, don't memorize these. So these three laws are combined to give the ideal gas law First, the ideal gas law is easier to memorize, and I'm not making you memorize it. But you can take the ideal gas law and use it to derive this information should you ever need it. So, finally, we can give you the ideal gas law, although depending on what chemistry you've taken previously, you're probably familiar with it. This is the PV equals N times R times T. And let's just get every definition here, right? P is pressure in atmospheres. V is volume in liters. N is number of moles in, well, moles. T is my temperature in Kelvin. And then R is the same as the one that we saw in the previous video. So 0.08206 liters times atmospheres divided by moles times Kelvin. Okay, so I want to talk a little bit about stoichiometry in gas reactions, and then we're going to apply that and the ideal gas law to a sample problem. So it won't be a big section because you already know how to do this. Because this is still just mole ratios. It's exactly like the stoichiometry calculations we did before. You just might have to use the ideal gas law to either get the number of moles or go from the number of moles to the property that you've been asked to calculate. So that's it. Actually, I don't have any points underneath that. I'm going to pause, get a sample problem written out, and then we'll take a look. Our sample problem says what volume in liters of H2 gas at 355 Kelvin and 0.971 atmospheres do we need to synthesize 35.7 grams of CH3OH, and we have the balanced reaction to work with. So in terms of a plan for thinking about what do we have, where do we need to go, we're starting with grams of CH3OH, and it's essentially asking me how much H2. So if we ignore the volume in liters and the temperature and the pressure part, and just think about how do I know how much H2 I need to put in, right? H2 is a reactant to get out the specified number of grams of CH3OH. Well, I know that if I can convert this to moles of CH3OH, I can use the mole ratio in the balanced reaction to get to moles of H2. So everything up until this point is exactly what we have done with stoichiometry in previous modules. From here, because I will now have moles and temperature and pressure, I can calculate the volume using the ideal gas law. So this last step to get to liters of H2 is kind of the new part that we haven't done yet. So if I set this up, 35.7 grams of CH3OH, use the periodic table to calculate my molar mass, and 1 mole of CH3OH is equal to 32.041 grams. From my reaction, for every 1 mole of CH3OH I get as product, I needed to put in 2 moles of H2. And this should give you 2.23 moles of H2. Now, ideal gas law, PV equals nRT, I'm looking to calculate a volume, so I really like to rearrange my reaction first, so I'm going to do that. So if I just divide both sides by pressure, then my volume calculation would be nRT over P. And so it's 2.23 moles times 0.08206 liter atmospheres per mole Kelvin times 355 Kelvin. All of that divided by, I have a very crooked divided by line here, but that's all right. 0.971 atmospheres, and this is equal to 66.85 liters.